Please confirm me.
Yes, sir. Change.
Thank you very much. Thank you very much. A very good morning to you all. Today we are with the power system operation and control chapter. Subject power system reliability and security we are supposed to discuss. Being the word reliability, it gives a very meaningful and insight of the particular operation aspect of the power system, where the ability of the system to be in service for the expected state or a duration is there or not. Suppose you have a power system which is an interconnection of several elements like generator, transformer, transmission line, and switch gears, loads, etc. Once they are put together, it becomes a connected system whose operation in stable or steady state is an expectation by the operational control. Then, to ensure the components which are connected are surely there to meet your requirement. Like a load of a certain hour is exactly worked out by the generator mechanism and is able to meet the requirement. Ability to meet the requirement of the end user reliably. The word reliability refers to the assurance of availability of the component to serve their intended duty. That can be measured by reliability component. So I cannot assure the component's reliability as whole. I need to understand reliability concerned to a generator, its ability to be there for a service for the current hour, next but 1 hour, next day, next week, like that. If I anticipate, if I predict, evaluate, it becomes a reliability aspect of that particular component. It may not be saved with the next component beside, whose reliability may be dependent on its own constraints like a capacity, ability, when it has been taken maintenance, when is the due of its maintenance, what is the load it is exactly going to expect. All these concerned contingent things define its reliability. Therefore, reliability of every equipment interconnected together define joint reliability of the system. So therefore, we say it is a probabilistic way of viewing the assurance of a system that it will be there to serve you. In that way, probability-based assessment is done in the reliability heading. Then, to support this, what is another aspect which is expected is security. The security, when we speak of, it is an ability of the system to be intact even after encountering disasters, defectiveness, failures, faults, etc. Or how secure is the system which is configured right now to overcome such contingent issues if so occur. The securedness, preparedness, the ability to overcome and be in operation, that aspect we considered as a security point of the measure, because every component is connected to a schedule. It is expected to serve its required intended duty and to be in service. So during its service, it may encounter so many difficulties, problems, failure, either internal or external. What is that preparedness? What is that inherent ability? Alternative to see to it that such a difficulty or disturbance arised will not be making it to be out of a system or not get damaged. So it's able to fulfill the requirement even after that. That securedness we call as a security aspect. It is an expectation. So security in terms of infrastructure, in terms of the components, in terms of interconnection and their ability, and over which assurance of availability of this entire connected system to be in service as a reliability of the entire system is measured. So therefore, these two have very close connectivity. Let us go ahead. So when we see a power system is an interconnection. like one diagram, single line diagram which is shown to you here, and having a basic intention of reliability to determine some probabilistic measure of undesirable events in the power system. The meaning of undesirable: when a system is put in service, it has taken care. Sufficient measures have been taken care by the designer and planner, have established the system for the anticipated load and for the possible causes which will affect the system's operation. In spite of that, anything which is unexpected under that way or during that planning or implementation, or during something which is just ignored, which will never be occurring, so that we consider as undesirable. It is never be occurring or never occurring, but due to the coincident or due to the certain parameter, it has really resulted. So such undesirable things which do occur, so we need to expect, we need to find a counter measures to address those them by probabilistic measure that come under reliability. For that we have a system. To this system we have a state selection. Then we need to evaluate the state of system. Then reliability indices need to be calculated. I have to see whether a system right now operation at hour number 1 is reliable. Will it be there for my next second hour, 6th hour, 12th hour, 24th hour, next 48 hour, like that? The system load is changing or decreasing or increasing, whatever the load change is occurring. Current ability, current operation is able to meet that or not. That if it is going to meet, what will be the state of that system at that time? I can evaluate right now. If the state of that particular hour, ability of the system to serve that expected load in the upcoming hours is a disastrous, then definitely we'll be knowing it well in advance. So for that, what are the measures? So many measures are there. I need to take care such that system will not be compromised. System will not get affected. For this, again, you have to recall back states of operation of power system: normal, alert, then you have emergency, extreme emergency, restorative, and a transition among them. Therefore, it is to evaluate, even after being in a certain state of operation, is the system reliable? Will be there for your next moment of service or next hour, like that. That is a probabilistic measure you are doing. We all clearly know what is the basic backbone of operation of power system: load flow analysis, study of faults, prediction, like that. This is another measure which is going to give you a estimation whether system will be there to serve or not. Will it encounter disasters, encounter difficulty before it is really occurring? You are going to predict it by probability measures, by taking care of components ability, evaluate the state of health of that by success rate, failure rate. Then what is the rate of failure? What is the rate of repair? What is the probability and what is the unavailability of the system? On that measure, we can evaluate the reliability indices for the calculation. Then for that, we have measures something like that: load curtailment is a success or it's a failure. So many measures will be there to just to connect it that entire system is viewed with a probabilistic way of measure of undesirable events. If so occur, what is the preparedness? What is the measure of that as a reliability index of that? So suppose it's 100% reliable. If I speak of a word, then it is to say for any power system being 100% reliable, it's the redundant. For every transmission line, if that fails, there must be a parallel line which is going to take care. If there is a generator failure, there must be a subsequent parallel generator running in parallel to that. If generator goes out, that is going to take care. That's called redundant, duplicating the entire system. Is it not a costlier one? Definitely. Reliability of a system, when we pronounce, it is an inherent ability and its operational maximization need to be taken. It is not to say simply duplicate the system, keep assured that never there will be a loss of generator, never there will be a loss of transmission, and like that. it won't be a scientific measure. Scientific measure says optimal. When the word comes optimal, it is a minimal set of usage of resources. So using that minimal set of resources, plan the strategy such that with that minimal set, it is going to surely ensure your expected reliability. In that measure, again, you have to account security aspect of the system also. You are not going to keep any component in danger, because when I ensure with the minimal set of component working to meet your requirement, I may be putting some of the component in stress, because the capacity of that may be encashed fullest by its capacity output or minimum by capacity. Then those get highly loaded, may encounter disasters or may encounter threats, failure in part or in full. So that should not be the case. I should ensure that no component in the system is kept in danger after my decision. In that way, all the measures I must take into account. So when I do it, then I'll be taking care of securedness of the system and the scope of that to ensure it will be there for your service or not, to what extent it will be there, to what extent it will not. That surely makes a scientific outcome to the percent which is not going to fulfill. That is the measure I should take. Is it really required? Then make an alternative. It can be an ignored, it can be curtailed back like that. So in this way, things go. Then when you measure power system reliability, let us go with the basic. As we are very clearly known, electrical energy or electricity has become basic commodity for the living. It is like our basic essentials of a life. It has become very essential, and the energy usage index is a measure of the country's growth in overall. So therefore, every corrected economic aspects or economy related to the country is connected to industrialization, the lifestyle, and the improvement. All those things are connected to the entire growth. Therefore, ensuring continuity of the service to the end user is the basic task. It becomes very necessary. Therefore, when it becomes very necessary, it is again viewed as a three sections: generating section, transmission, and distribution. Hierarchically, it is organized. Then when it's organized, it becomes very necessary for us to assess the reliability of generating system, assess the reliability of a transmission and distribution like that. Therefore, once the reliability is to be evaluated, it has to be functionally divided into some sections like generating section, transmission, and distribution like that. Now moving to the next coin world, reliability of a power system is generally designated as a measure of ability of the system to provide customers with adequate supply. The word adequate has come here. What is this adequacy? Adequacy, nothing but the installed infrastructure, mechanism, the associated components which are integrated should ensure the requirement. Suppose a certain megawatt is your demand. Do your installed number of generator, whatever we have, are able to collectively provide that megawatt? Yes. Are they able to cope up certain delta megawatt? Suppose there is a small step change. Is it adequate? That way, adequacy comes into picture. We have to take care the installation of the component or the components which ensure you for the current plan. In that way, adequacy comes to the requirement. It is a primary performance criteria of the power system. We know it. Usually, power system ensures or find outages and which are very significant and will definitely affect the economic issues connected, and they impact very badly the end user and utilities as well. Because when there is a disaster, when there is a uh, breakdown, the corporations suffer because they are utilizing the resources. They cannot stop like an end user. They need to burn the fuel. They need to keep their mechanisms working, but they cannot encash it by delivering it to the end user. In that way, even they also get affected. Therefore, the planning, power system operation, and all such environmental conditions, adverse effects, and maybe a blackout, all such issues need to be taken care before you define reliability in that service system. So this is how reliability comes into a basic definition. Now, when a reliability is so important for the corporation to assure itself, then how we can think in a different way. One is, how much do we spend on, and is it worth? So on the reliability only, somebody need to do study. The corporations which have put money, material, and resources, they have to really think of this. They cannot simply keep quiet after having installed the system. It's running. It will do something for me like that. It cannot. So we have to spend some money, the earned money. We have to spend as an investment to understand whether a system is reliable now, will be reliable in the future, to what extent, to what time of the particular operation or duration is considered. So there must be study performed, research need to be performed, planning need to be worked out. That's what we have to do. By what factor do we increase reliability? The another interesting factor is, we know the current system integrated capacity. Suppose it is working very nice. Certain reliability say 85% reliable. 15% is the margin. Due to one or other kind of marginal failure, system is not able to cope up 15% of its scope. Then it's a 85%. When I say, do you keep it as a 85% only future also? Do you have any plans to improve the reliability system to make it 90%, 95% like that? So to what extent you would like to increase the system's ability to meet the requirement of the customer? That what the corporation need to focus this, because they have to be in the business. It's an trading. Therefore, to what extent we need to increase? Then it's an investment in infrastructure, growth, technology, and all associated switch gears. Everything need to be taken care. So this is an aspect the power system need to plan. Then, can reliability be allowed to degrade? This is another very challenging task on the power system operation and control. Can I compromise simply? Today, the system which is installed having certain capacity, able to cope up the loads of today's load, and by next 5 years, due to the growth in load, definitely I would have taken an upgradation of my system, installed generators, transmission mechanisms, switch gates, upgrade, modify like that. If I would not have done this, surely my system would have experienced a difficulty, problems, failures, and I would have compromised the reliability to a very lower value. Can I allow it? Is it acceptable to the customer, acceptable to the corporation? Definitely no. A degrading effect. When a customer service is not fed or met properly, customers shift from one to another like that, because the open market like a trading, definitely I will not purchase the power from you. I'll go for bidding with a neighbor corporation or another one for my reliable operation. In that regard, degrading component of the reliability shall be seriously thought. It should be seriously thought, so that system need to improve its reliability, at least to maintain and improve. That's what they should do. This keyword degrade says compromising it from the current to the lower side. It should never be given a chance. Then who has to decide on the level of reliability? I was speaking about, do we need to increase the reliability? Yes, it is an expectation. Is it worth to spend on this? Yes, it is worth to spend, because we are expecting reliability. A revenue generation takes place here, additional revenue, and component degrade should never be allowed. Then who will decide this? It is the connected corporation, infrastructure to whom it is interconnected. All together need to think. It is think that I am only generating setup. My setup is only generation. I am depending upon somebody who is a transmission agency. If transmission agency's reliability is not comfortable with me, even though I have best reliability scope from generating point of view, can I meet the end user reliably? Definitely no, because the mediator is the transmission agency. His or her reliability is lesser than what I am possessing. Definitely my actual reliability will be the lowest probability of the connected system. Therefore, it is to be decided very judiciously. I cannot define my own. My own may be good. What about the connected to me and serving next one? So joint reliability appear there. In that way, we must think very carefully. In that due respect, from all these four question viewpoint, we have to understand reliability in these two major things. One is system adequacy, system security, like this way. Let us move with the adequacy. As we have just focused, system adequacy involves existence of sufficient facilities, infrastructure in the system to meet the requirement of the customer's demand. The facilities include generating capacity to generate enough energy, transmission, the transmission systems and the distribution systems connected to the controls or any, you can say, the infrastructure required, so that adequacy involves static system condition rather than the system disturbances, and is affected by many factors such as installed capacity, size and unit availabilities, maintenance requirement, and interconnection, and so on. So basically, adequacy as such, you can look as an infrastructure which should be there to justify and support your required task. So therefore, it is a static control. It is a static phenomenon. It should be there or not. If it is there, you have a scope to think. If it is not there, definitely there is no scope. Therefore, adequacy comes as the basic backbone of your reliability measure. Then security aspect of that. When you have everything available with you, put in service, do your service schedule what you are running is secured, ensuring the security of every component interconnected, endeavoring its service, a transformer, a generator, a transmission mechanism, a distribution side, any safety regards, security aspects which surely protect the system, or system is put in danger on an occurrence of a fault. Is there any measure for that? Is there any protection provided for that? Is there any protection for a generator? Is there any protection for a transformer? Or have you really thought of? So that securedness come into picture as security system, which however concerned the ability of the system to respond to the disturbances. The power system have to maintain certain levels of static and spinning reserves in order to achieve a required level of adequacy and security. So this become the operational aspect, scheduling of the individual component for your required main task. While doing so, no component should be put in danger, because a power system being very dynamic in nature, off and on disturbances do occur. There will be a continuous rise and fall of demand. There will be certain dynamic changes working in the system. So your system must be able to cope up with those contingent changes. If not, system is put in danger, at least a component fails in part or full. The subsequent component depending upon that, depends on that, start malfunctioning. Once a cascaded failure protrude into a healthy system surely get affected by the a minor or a major fault, which is going to threaten the security. Once the security is threatened, even though you are having the sufficient infrastructure in the system, the operational aspect being threatened, your operational total control will be in danger. In that due respect, both adequacy and security need to be judiciously worked out. We shall not overcome, we shall not simply overview. We have to really work so that securedness of the system is there or not individually, using contingency tools, security control, optimal power flow, any fault study have to be combined such that they keep on assessing the health of the system from security perspective. Once a security loop is ensuring you are good with the current operation, probable changes are really going to cope up or is going to cope up with those also, then securedness is there with the system. In that due way we need to go. Then I was just speaking about the system security refers to a system to meet demand under dynamic disturbances in the system. Let's see one simple N-1. I call it as N1. N1 criteria means, let us imagine there are N systems in your corporation. If any one component go out of your control, means N1. Some people read it as N minus 1. It's also same thing, means out of the N, one goes out of your control. Whatever is that. N1 criteria refers to a situation one component out of the N integrated goes out of your control. How is that system left? Is in danger? Is it secured? Able to cope up with the changes what it is experiencing right now? So if it is able to cope up, definitely your system is N1 criteria acceptance. Likewise, it is a one I said, it can be N2, N3, Nx at the end. That makes the system security. Even a two component goes out, system will be intact. Six component goes out of the control, system is intact. So this kind of assessment analysis with the security perspective need to be performed in the computer, in the energy center. That ensures the state of health of the system for upcoming any contingent changes. So that kind of measure, NX criterion based measures need to be taken as a loop. That loop is always keeping an alert. If that fails, if this component fails, if certain component together fails, what is the impact of that failure due to internal failure, due to external failure, or its own aging effect, whatever. So that remaining system, left off system, is in danger. Is it secured? Is it going to meet the requirement of the power system or not? Or what are the alternative to meet the loss of that should be studied. So that quantifies the reliability, because we are defining reliability as an ability to be there in service, to be in service for the expected state. So for that, infrastructure support is highly needed. Then infrastructure support is assessed by secureness of the component which are in service. This way, these two are connected to one another. Now, so when we have this particular security assessment or security analysis and reliability analysis together, entire power system is hierarchically classified into three sections. I just come to the important section of this as HL1, hierarchical level 1, only the generation setup. Hierarchical section or level 2, concerned only with the generation and transmission. Hierarchical level 3 is concerned with all the three sections as in generation, transmission, distribution. So evaluation should go in different way. So this is called assessment of adequacy. Means I need to check whether the installed system components right now together put in service are adequate for my schedule right now and a future plan. To what extent this will support my commands. To know that, assessment need to be done. To assess that, you have to take a zone of your assessment. Those zones are classified as 3, HL1, hierarchical level 1, HL2, HL3, like that. That's what is put in this content on the presentation. Let us go what is HL1, what is HL2 in the next slide. Like this, I'll be going here. Before going to do that, let us see one more view of that. How the security of the power system is viewed. This one interesting question. What is security of a power system? What is security analysis of a system? What are all the different levels of security would be a one question you may need to you may get, and you need to answer very significantly like this. Therefore, security is an expectation. Security is an ability of the system to be intact even after encountering fault, disturbances, and disasters. That is to ensure from infrastructure perspective, like adequacy viewpoint. Then that ensures the system's stability for assessment of your reliability. Then system must be there for your control. Then based on that, severity of the problem or based on the difficulty level, system may find different states of operation. Now you have to connect yourself. States of power system, how we classify, like a normal state, alert, emergency, extreme emergency, restorative, like that. Similarly, we have security assessment by security levels. So those security levels are likely in the energy management. It is assessed by security algorithm or loop, which is like this. Level 1 security means it is called as secured mode. Level 1 is secured. We should not confuse these six headings with states of power system. This is security assessment and security levels. Therefore, level 1 is a secure. At this level, entire load is met without violating any of the constraints of the power system component. Generation and loads are perfectly in balance. No component is overridden or no contingencies will cause any violation. System is intact and balanced. This state we call as secured nature in security assessment. When I run the security loop algorithm, it will evaluate the state of health of a system from the security perspective. Then it is said to be perfectly in balance. No component is having a violation. Every load is addressed and perfect balance of delivery and generation and losses are accounted. This system, this state is assessed as secured. That is called level 1 of security. Then it may not be the continuous state of observation due to some changes in the load because of dynamics, due to some internal or minor variation in the input to the generator or changes in the parameters of the transformer. There will be this minor change in its operational level. That's called correctively secure. It is secured. Nothing is lost as a service, but there is a minor shift in their operational node that we call as level 2, correctively secured. All load is supplied without violating any limits as in level 1, perfectly balanced. But contingencies one do not cause any load loss. There is nothing is lost as a load delivery. If an appropriate control action is taken, it is more economical to run the system at this level rather than level 1. But it relies on corrective action taken. Post contingency, these action can be determined by a priori. Well, before it is occurring, we have to anticipate, keep remedial. That's called a priori. A priori refers to a mechanism or a schedule keeping or kept ready for a certain problem. What is the cause? What is the remedial for that? That measure is called as a priori by running optimal power flow, including security constraint. I mean, correctively secured system is just level 1, but minor variation in the operating state of the component is noticed, but no load is compromised. No component is overloaded or violated its limits. That state of operation we call as in the security level 2, correctively secure. We can bring it back to secure state by having adopted the correction to the respective operating point changes. So this is how we have to work it out. Suppose another mode is called level 3, alert. Here load is still supplied without violating limits as in level 1, level 2. So in level 1, level 2, load and generator, transmission system, everything is interconnected. Even in level 3, alert state, all are interconnected. Load is supplied, no violation of limits, but contingency cause some violations which cannot be corrected without loss of load. Can you see this statement? The system can be brought back to level 1 or level 2 by preventing or preventive rescheduling. So alert state is nothing but load is connected, but there is a minor compromise. So it can be brought to level 2, level 1 by having taken preventive rescheduling. It means there is a chance that contingency analysis. What is a contingency? Contingency is an unexpected event or instant disturbance which may occur on the power system. From the operational aspect of that, we take it as an input. Suppose such an disturbance, such an variation occur really in time. What will be the impact of that on the system? What is the remedial to reduce its impact or to eliminate the cause of that? For that, we have to have remedial measures kept. That's called analysis of the system from contingency, which is unexpected. It may not occur sometimes. If it occur, what is the remedial for that? In that way, when you are in level 3, you are running system neck to neck or connected one to one such that load is perfectly connected to the system. But certain contingencies, if they really occur, make the system to lose some loads. You may need to reduce the load. You may need to remove some of the uh, non-critical or certain heavily loaded loads so that system will be in alert. Otherwise, system will not be under your control. That's called as alert. It is a noticeable change from the operation of either level 1, level 2. There is some chance that certain disturbances really occur at this time of operation should be corrected only by compromise of load. That's an indication. For that, action is rescheduling. The load growth is off. Imagine you are in level 2, correctively secure. Everything is interconnected, intact. Suddenly, load growth occurs. Load is increasing. You are not yet taken any generation side generation increase. So load is increasing. Generation is still static. Then either you need to generate more or you need to control the load. That's called as alert state. So you cannot maintain balance unless there is a loss of load if you don't want to change the generation. Generation is static. Loads are growing. Then what? How do you balance the P and Q? Only by compromise of load only. That can be the view of alert. Correctable emergency. In this level 4, here all load is supplied. See here, this is the information what we get from level 4 is load and generator or all the system is intact. No islanding is occurred, still intact, but with operating limits violated. You can see here. All the loads are connected, generators, transmission mechanism, and distribution setup. Everything is ready, intact, serving the load, but some violation is running up. This may lead to failure. So it means with the operating limits violated. So these violations cannot be corrected without the loss of load. You can just imagine a particular power transformer or a critical distribution transformer is loaded capacity at plus side. System is closed. You are meeting the load, you are have a generation, system is intact. But any further increment in load definitely damage the transformer if you're not going to protect it. That way, it is just loaded and its operating constraints are just violated, but system is still closed. If you continue like this only, system may enter non-correctable emergency. It means it is very critical if I continue further. For that, to retain that component functional for the future, I have to compromise the load because that component ability is challenged. You are running beyond its capacity. It's performing for its overload duty. Then further continuation of that overload may damage the component it itself. Therefore, we need to reduce or delete or some removal of load is the only way to do it. That's called corrected without loss. Cannot be corrected. We have to correct it by removal of load. So system can be brought back to level 3 by proper corrective action or some proper planning need to be done. It is called correctable emergency. System became fully loaded, violation of limits is noticed, but still system is closed. Next moment, any further change may cause a disconnection, failure. So before going to that, corrections can be done. That is to bring it back to previous level 3 by removal of load in this regard. So another state may be level 5, non-correctable emergency. Look to the information. All loads are supplied with violation of operating limits. Most of the components are on the verge of trip. They are violated. Surely at any moment they may collapse or they may fail. The situation can be corrected only by loss of load. There is no solution. The only solution is just to reduce the load, remove the load itself. The duration and amount optimized by an optional power flow program. You can you can calculate this non-correctable emergency has really gone. Every component is really out of your control. The moment next change as a load is noticed, system is sure to collapse. In that situation, your computational algorithms help you. The optional algorithm, suppose to get back to at least a controllable state. What is that portion or a percentage of the load and part of the load I should remove so that system comes back to my control and I can retain operational aspect and infrastructure to a good health. So that can be run as extreme case optional power flow program. So we have seen load flow program. We have seen short circuit study. We have seen stability study. This is optional power flow program. I have to devise something at extremity. What is that critical trial I can do? By having tried this, system comes back slowly under my control. I can recover the operational control of that. This way you can look. The last state of security is level 6, restorative. Operating limits are not violated, but the system is operating with the loss of load, restorative control, bring it back to level 1 not 2. This is called an in the power system state of health, restorative phase. You can recognize that state here. This is called power system loads are disconnected here. Already many loads have got disconnected. Generators which were functional, they are running. Some part of the load which are connected being met, and definitely that connectivity is safe, but not the original connectivity earlier. Therefore, this is called a restorative phase, part by part reconnection and reconfiguration to bring it back to either secure or correctively secure state here. Therefore, this is one interesting question you will get. So all the levels in brief, 2 to 3 statement you need to present per question, per heading of this level. That makes one sense of security. This always repeats. And coming to the adequacy measures, how it is measured. I was speaking about adequacy measure is done by 3 way. One is the inner rectangle. You can just see here this rectangle, functional zone 1 itself. This is only generation, hierarchical level 1. Then if I club transmission and generation, zone 1, zone 2, if I club it, it become next triangle. Can you see the dotted triangle? That become hierarchical level 2, HL2. Then if I superimpose this with the previous generation, transmission, distribution, together it is the outer dotted rectangle. That become hierarchical level 3 and HL3 level. And what is the meaning of this? In the functional zone 1, the adequacy measure assessment of some critical parameter for the reliability measure is done only from the generation perspective. Hence, the parameter which we assess, use, evaluate are only generation system based. When I use level 2, it's a combination generation and transmission together combined to give the reliability measure of the system. When I use a complex system, complex in the sense level 1, zone 1, zone 2, zone 3 combined, that's become hierarchical level 3. Then parameters what we measure in zone 1, zone 2, zone 3 are different. So in that way, assessment should go. So adequacy assessment in hierarchy level 1, level 2, level 3 are different. There are certain parameter mentioned. For zone 1, only generation assessment, what are the parameter? Zone 2 assessment, what are the parameter? Zone 3 assessment, what are the parameter? Likewise, combination is put as HL1, HL2, HL3. That we can be seen here. Clear? Let me go here. HL1, adequacy indices. For this, it's very interesting. There are about 6 parameters. Loss of load expectation, LOLE. Loss of energy expectation. Like just I outline first. Point number one, point number two, point number three, point number four. These are the four important indices which come under HL1. What is HL1? HL1 is an adequacy indices or a measure in only generating setup. Zone 1. This is zone 1. Come back. Zone 1. When I measure adequacy of zone 1, what are the parameters I consider to evaluate the adequacy of the system? That is what is here. So there are many indices defined at various hierarchical levels. For that, let us say 1, HL1, loss of load expectation, LOLE. This is measured in hours per year or days per year. It means the system, generation system is unable to serve certain number of hours in a year or certain number of days in a year is a unit of this, which is defined as LOLE, loss of load expectation, is sum of summation I belong to S states, set of all the system. There are S systems. I belong to S. Probability of I loss for the duration T. So it is Pi into T summation. Let us see where S is the set of all the system states associated with the loss of load and Pi is the probability of system state I. It means to say we have S set out of which I state. At I state, certain component fails for a duration T. Then what is that probability that that state is going to occur? 10% probability, 50% probability, 80% probability that that loss is sure to occur. In that regard, probability of occurrence of state I with T that we measure as where S is the set of all the system states associated with the loss of load and Pi is the probability of that state. So usually this is accounted. It may be in the particular ith state, maybe in a month, in a day, in a week, or like that. When I measure, it becomes a gross value. What is that? The generation system really not there for your particular loads. Certain loads say so much of megawatt for so many hours of a year or days of a year. So this is going to be measured. If it is an hour per year, Pi depends on comparison of hourly load. When I measure it as hour per year, Pi probability of that ith state become hourly base. Then definitely this index does not indicate severity of deficiency. It is just going to give you when is that it is not available. That's all. How many hours of a day, how many days of a year system is not able to meet your requirement is an indication. Is it not an important aspect for us? Because when I have my system generations put together in service, I know the capability of the system, its min and max capacity for a dynamic schedule. If I know this, loss of load expectation, certain hours a day or certain hour a year or days a year, if my connected system is not able to meet the load of a particular requirement, then it becomes an issue. This parameter I keep in reference. Suppose this is my definition. When I quantify reliability, I take care this much of hour a year or days a year. This component is not there for my service. How can I ensure my reliability considering this as an available to me? For that reliability assessment, this is going to support. Therefore, loss of load expectation is an measure that system is not there for your service like days a year, hour a year, like that measure, whose probability need to be evaluated. Then loss of energy expectation is called load side. Energy expectation, LOEE, it's a megawatt hour per year. You can just see LOLE is summation of state I out of states S. 8760 number of hours in a year, CI, particular loss of CIth hour into probability of that state PI, where CI is the loss of load for a system state I. So it is a measure here, energy loss, expectation of loss of energy, LOE, megawatt hour per year. It means CI is the loss of load and the state is at ith state. This index is expected energy which cannot be supplied because the demand exceeds the generation capacity. Now see, this is a very interesting factor. Certain generating plant is having 5 generators. Total capacity of the generator is known to us. Due to a certain situation at certain hour, due to a maintenance lack or due to the maintenance schedule, or due to the internal failure or due to the minor fractional failure, you cannot provide the capacity which is required for the meeting. That time, LOLE is the measure of that system at the max, at the worst possibility. My power system, generator system, will not be able to cope up for these many megawatt hour in a year. That's what is a measure. That is, that particular state is criticalness that cannot be supplied due to my maintenance schedule on a particular month, due to the failure which I expect in that way. So that is measured as loss of energy expectation as summation of a state I belonging to state S, 8760 into loss of load into probability of that state I. So when I multiply in a year 8760, I'll be getting account that total energy. It's the loss of power into energy, duration, power into time. It's the energy. This is an indication. This is a very interesting factor to evaluate energy index of reliability. This is measured. This is used to define EIR. Whatever is that. Just say another important aspect of HL1 from the generating perspective is LOLE. The next is loss of load frequency. When I measure how frequently loss is happening. So it is where LOLF, number of occurrences per year. Loss of load frequency, how many times the disconnection of load or non delivery of load to the system occur in the form of rate. We call it as loss of load frequency. It doesn't mean hertz. It mean for me occurrences per year in that way. LOLF, number of occurrences per year. It is measured as sum of all the states like I belongs to S, wherein capital Fi minus lowercase fi. What is this? Just see here. Where Fi is the frequency of departing system state I, and F lowercase I is the portion of Fi which does not go through the boundary between loss of load state and no loss of load state. It means this is the measure how many times there is an loss of load to the particular system, and it is measured as the frequency of departing, means system which goes out of your control, definitely not there for your service, that we call as frequency of the departing system. What is its inherent ability to be in service, to be not in service? We call it as reliability of that component. If I consider reliability of that is 100%, if I speak, definitely it will not go out of your control. If reliability is 50%, so any time of its operation, like an base to duration of observation, 50% it may go out of your control. Like that, Fi is the frequency of departing system, which is state I. And Fi, lowercase fi, is the portion of Fi, part of this Fi, which does not go through the boundary between loss of load state and no loss of load. So this way, If I take a measure, summation of I belong to S fi minus lowercase fi give me number of occurrences per year in this way. This is also an indication. Is it not an interruptions per year like that? Suppose there are 50 interruptions per year. Definitely 50 become a miserable count, because in a year 50 times there is an non-delivery of load to the requirement is a measure of 50 like that way. This is called frequency. Likewise, if I say it is very low, it is to ensure system is more reliable. In that way, this number of times the load not being addressed in terms of number is a frequency being addressed here. The next parameter is loss of load duration. How long there is a disconnection. In the parameter number 3, we get how many times in a year. But in the next parameter 4, loss of load duration, LOLD, it is hour per disturbance. If there are, say, 10 disturbances in a year, what is the disturbance hour per disturbance? Is it really 1 hour a disturbance? Total 10 hour a year. Example, there are 10 faults, 10 disconnection in a year. How long each disconnection result you? So 10 divided by 10. If I say 1 hour per disturbance like that. In that way, this give me the duration that the disturbance sustain remain in practice, though that there will be a disconnection of load. So LOLD, loss of load duration, is equal to LOLE. What is that LOLE? I go back here. Loss of energy expectation, measure of expectation of loss of energy, megawatt hour a year, megawatt hour a year, LOLE, divided by LOLF, frequency, how many times a year occur. So total loss of energy divided by total number of instances of disconnection. If I take a ratio, that give me the duration per disturbance. This is what LOLE over LOLF refers LOLD. So this is a measure. Suppose there are 10 disconnections. Each disconnection is of how much duration is measured by LOLD. Surely, if there are 10 disturbances, each by an hour, there are 10 total disconnections or 10 energy hour disconnected like that. So we can just measure reliability of the system by adequacy measures. We call them as adequacy measure of HL1, hierarchy level 1, and LOLE, LOLE by loss of energy expectation, LOLF, loss of load frequency, LOLD, loss of load duration. So these four parameters describe the adequacy measure of the generating system HL1 hierarchy. Suppose if I go to HL2 adequacy indices. Now I am combining the generation aspect with the transmission aspect. I should be in mind. So generation and transmission together I am defining as a complex system. Then the measures will be different. I'll be taking care of generation, I'll be taking care of transmission ability as well. Then the first parameter what we measure is probability of load curtailment, PLC. Probability of load curtailment refers to sum of all the states I belonging to S, probability of loss of that state. So there are 10 states in a year, example, or a 12 state. Every month is one state for you. 12 is your S value. So what is that probability? The particular month one state is repeating, state 2 is repeating, state 3 is repeating. So in that way, probability of loss of load or load curtailment, if I sum up, that give me a quantified value as a PLC, probability of load curtailment. We can see here where S is the set of all the system states associated with the load curtailment, and Pi is the probability of state I. So more of probability assessment only, keywords need to be understood. Okay. Expected frequency of load curtailment. EFLC. It means frequency of load curtailment. Now it comes with the time, how many times, numbers per year, like that. So EFLC become occurrences per year. This is same as LOLF. If I go back here, LOLF, this is how. So how many times a particular state of a departing machine departs out of the non-departing portion. So this difference is giving you as LOLF. The same way it is mentioned here. Okay. Expected duration of load curtailment. Now it comes with when we have a count here, when we have load here, I can definitely come with the duration. Expected duration of load curtailment, EDLC, is hours a year. So how many hours disconnection is measured, or disconnection is expected? That is called EDLC, expected duration of load curtailment, as PLC, probability of any state I into 8760 as a annual hours in a year. By multiplying, I'll be getting EDLC, quantify you as how many hours a year there occur curtailment of load. So the previous one give you curtailment or occurrences per year, like that. Again, I have average duration of load curtailment. Again, I'll be counting per disturbance or per curtailment or per disconnection. How much is the hour? You can say ADLC. ADLC refers to total curtailment, which is EDLC, PLC into 8760 divided by frequency. If I do EFLC, this give me how many hours are allocated per disturbance, like that. So therefore, very similar parameters like the HL1, but here I'll be taking care of both generation and transmission joint. Therefore, ADLC refers EDLC over EFLC as a measure. So once one need to practice these keywords because they look very alike. The meaning is very alike and the presentation of them under the HL1, HL2 just differ. So take care of this carefully. Then expected load curtailment, megawatt year. This is what is that expected load curtailment due to generation side or due to transmission side as a joint. It is called ELC, megawatt per year, which is sum of all the states I belonging to S, CI into FI. And what is CI FI? You can see here. CI is the load curtailment in the state I. FI is the system state frequency. What is that? Frequency of occurrence of state C, where load curtailment is possible. So it is called as frequency and duration based assessment of reliability. In the previous semester, FAD, we have assessed availability, unavailability with lambda and mu, availability rate and unavailability rate, and probability of a state, unavailability of a state. We have studied it. Similarly, we have measured another state called as FAD, frequency and duration based assessment of reliability. Under that, frequency of transition from on state to off state means working condition to a failure case, or off to on state, failure to after repair coming to online is called return. So on that rate of transition we define as a frequency. So on that basis, the occurrence of a state I, which is a C load curtailment, for the frequency of that is Fi. When I multiply them and add them, such all possibilities, that give me ELC as my requirement. Similarly, when I go with the next one, expected demand not supplied. See here, now I was having a generator. When I am having a transmission system involved, parameters are increasing. Then it is EDNS, expected demand not supplied. It was expected to deliver, but not being addressed due to so many contingent issues. That is called as EDNS. It is measured as probability of a state CI, probability of I not being delivered. So much of megawatt is not delivered. CI is the megawatt not delivered at state I, whose probability is by PI. PI, CI give you the net megawatt not being delivered at state number I, state number J, state number K, L, M, up to S. If I accompany all those as a summation, that become total megawatt not at all being served by the system. That is called EDNS. Expected demand not supplied. It was surely being addressed due to contingencies, due to any other aspects affected. It is not being addressed. What is that not addressed? Then we address by probabilistic way of not being addressed by a certain value at our I or instant I. Probability of that, if I multiply, that quantifies me megawatt not being served. Such how many times, how many are there states? Account them as a summation that become quantified megawatt. The another is expected energy not supplied. See here, here it is power not being supplied in megawatt. Here it is megawatt hour energy not supplied. Can you see this change here? The same parameter into 8760 is multiplied here. Just to account hour of a year. CIPI into 8760. That's all. This is called EENS. Expected energy not supplied. Megawatt hour a year. So this need to be seen. The eighth parameter is transmission perspective. Bulk power supply, average megawatt, curtailment index. See this meaning here? Bulk power supply, average megawatt curtailment index, BPACI, megawatt per disturbance, not being supplied. Then you must have total megawatt totally not supplied. How many such instances were there? If I take megawatt per disturbance comes as a parameter. BPACI is ELC. I go back. What is ELC? ELC is expected load curtailment, which is not being met in a year. Megawatt per year. Total quantity of megawatt in terms of power not being addressed in a year, divided by EFLC. What is EFLC? You can just see here. Expected frequency of curtailment in terms of number of times not being served. So total energy not served, total times not served. So energy by how many times it is not being addressed. Ratio, if I take it, become the bulk power supply average megawatt curtailment index. That is becoming megawatt per disturbance. Per disturbance, what is the loss? This is the what is the average. All these are average values because we are taking disturbance at the denominator. Number of times that is disturbance is in the denominator. So this is about the joint adequacy measures of HL2. Similarly, I have HL3. HL3 is again still complex because HL3 refers to, I go back and come to this point. HL3 refers to what? Entire system. It is equipped with zone 1, zone 2, zone 3, nothing but generation, transmission, distribution, whole together we are calling it as a hierarchical level 3 HL3. Once you are measuring HL3, the parameters are again taking care of distribution perspective, transmission perspective, and the generation perspective. That's what is all the three are complex connected here. Indices in distribution system are more complex to calculate, and some of the indices used are defined like SAIFI, system average interruption frequency index, system average interruption frequency index, SAIFI, which give you unit interruptions per system customer per year. You can see here interruptions per system customer per year. So there are so many customers connected to your system. Say 10,000 consumers are consuming power from your system. There are so many interruptions are occurring entirely in your system. Maybe industrial user, maybe domestic user, maybe corporate user. Variants are there in your system customer perspective. Total interruptions are known to you in a year. That is called interruptions total divided by type of customer per year. This is what is the measure that is given as SAFI as, you can just see the numerator, summation of state I belonging to R lambda I Ni divided by summation I belonging to R Ni. So let us see what is this. Ni refers to number of customer at load point I. In a system, there is maybe a point 1, point 2, point 10, many corners of which connected user. Maybe you can imagine distribution point of view, a electric pole. From that pole, so many consumers are getting connected to the service. So let's say at that pole, there are 10 consumers, though N stand here 10. Then I stand one of the 10. Suppose house number 1, house number 2, there are 10 houses connected to a pole. If I say 10 is the denominator, out of the 10, which is the number you are trying to assess interruption rate per consumer, then N need to be total, I need to be a particular state when you want to measure. So that's why N become number of customer at load point I. Then what is this lambda? Lambda I stand as failure. So rate of failure, you have to recall back the rate of failure and rate of repair. So these two are complement to each other. So lambda plus mu, if I count, it becomes 100% in probability approach. Therefore, what is that rate of failure of any load at a particular point? Then definitely I can measure net failure divided by number of connected user. Similarly, what is R? R is the set of load points in the system. R is nothing but if there are so many total connected load points, at each point I have n consumers. Think that there are 10 poles. Each pole is having a 10 connection. Total consumers are 100 then. In that way, R is set of load points. At each load point, I have 10 consumer given by n at 1, 2, 3, 4, I. And lambda I refers each consumer's failure rate. Lambda I is what? I is each customer or consumer. So whose failure rate if I know? I can compute SAFI. System average interruption frequency can be computed as, you can see here, total interruptions. You can see the numerator is lambda I and I. What lambda I says? Failure rate of a ith consumer. Of what? Ni, nth pole or nth load point. Then divided by number of load point n. It gives you the numerical data interruptions per system consumer per year. So this is going to be one of the important aspect of adequacy analysis of a complex system. HL3 SAIFI. This is an average because industrial loads, corporate loads, and domestic load, like in a combination mix, if you consider at a load point, definitely this is a mix. The duration of failure or rate of failure of industrial, corporate, and the domestic things may be different. It is an average. Then I have system average interruption duration. When the number of interruptions in a year, if I know total interruption in hours, and if I know total number of interruptions, if I take a ratio, it give me hour per system customer. Like this we can see SAIDI. SAIDI refers to UINI, sum of all ith instances out of R. You can see annual unavailability or outage time in hours per year is a U for any load point n. So when I sum them for all the load points, n is 1, n is 2, n is 3, n is up to R load points. At each load point, so many consumers are connected and each is having outage. Annual unavailability is known to us as hour per year. This load point cannot supply the load to the consumers. So each load point is having UI, unavailability rate, hours per year. Multiply with the NI, all the load points, sum them, that become total system hours of unavailability divided by system customers, sum all the customers. What is that? Summation of n I being 1 to r. So when I take a ratio, it becomes hour per system customer per year. So what is that disconnection experience by each customer in a year is given by this parameter. Then customer average interruption frequency, CAIFI. Again, you can see the unit interruptions per customer affected per year. Now, a small difference you will see. Lambda INI, as usual in the previous case here, lambda INI interruptions total divided by customers affected. So what is MI here? Number of customer affected at load point I. Here I am taking care of load point. If there are 10 load point number 1 I consider. Out of the load point 1, who is that affected most out of the 10 connected consumer at pole number 1 or point number 1? I would like to see impact of interruption on that consumer 1, consumer 2, consumer 3 like that, or load point 1, user 2, user 3 like that. I can evaluate. It's called as interruptions per customer affected per year is given by total interruption divided by number of connected consumer at load point I. This ratio give me CAIFI. So for me, you all need to just take care of a heading which is bold here. One parameter you have to write. This is what is you have to write, and same thing you write by text. One line or two line you have to mention what is the meaning of this. Then customer average interruption duration index, CAIDI. I'm coming down to per interruption, how much hour is spent. That's called as hour per customer interruption. CAIDI is SAIDI. What is SAIDI? You have here system average interruption duration index. So the hour per system consumer or customer divided by SAIFI. So SAIFI was the first thing here. It is a system average interruption frequency. Total interruption and interruption frequency. When I take a ratio, that becomes hour per customer interruption. Let's see. So therefore, these are the, and this is another important aspect of joint measure of HL3. So by this way, we have come to a discussion of HL1, HL2, HL3. This is how 3 different questions you may get here. So take care. This is very interesting question.